Hello everyone, my name is Joshua Klein, and I am a doctoral student at the Swiss Federal Institute of Technology in Lausanne, Switzerland, or l'École Polytechnique Fédérale de Lausanne. Today I'd like to introduce you to gem5-X, as well as premiere our gem5 extension for RISC-V full system simulation. This session is the first in a two-part tutorial series here at HiPEAC 2021. This first session is aimed at those who do not have or only have very little experience with gem5 and are interested in the practical aspects of using gem5 for their research. I would say that if you're already familiar with gem5 and or gem5-X, but you are interested in learning how you can use these tools to optimize architectures, that you should take an extended coffee break and come back for the second session. In this first section, I will introduce you to both gem5-X and GXR5, walk you through your first benchmark run, and then cover some useful techniques and features you can utilize to improve your workflow and productivity. In the session that comes after the coffee break, I will explain how you can extend architectures in gem5-X and GXR5 for architectural exploration. So in case you missed the earlier lectures, let us briefly cover what is gem5 and why would you use it? So as a system-level computer architect, I am interested in the performance and energy ramifications of rearranging, extending, or modifying existing computer architectures to address the gap between memory and compute performance, otherwise known as the memory wall. In particular, my research is focused around RISC instruction set architectures and integrating emerging in-memory compute and near-memory compute technologies for AI applications. As a result, I need the ability to quickly prototype, reconfigure, and simulate new computer architectures while also obtaining valid performance statistics. So as visualized in this graph, if I try doing my work with HDL in an associated simulator such as Verilog with Vivado, I will get extremely accurate performance results with respect to real hardware. But as anyone who has worked with HDL will tell you, I will have a lot of overhead, both in terms of the development and verification time of the new architecture, as well as running high-level applications. On the other end of this graph, I could use a functional simulator such as QEMU, which will provide me with functionally accurate results very quickly. But because intricate hardware subroutines are not implemented or simulated, I cannot rely on QEMU to give me accurate performance statistics. And therefore, I need something in the middle of this graph here. Something with just fast enough simulation speed that I can still obtain valid performance statistics so that I can prototype and explore architectures quickly. And so this is where gem5 comes in. gem5 is a highly modular and extensible system-level computer architecture simulator, and it represents a middle ground between the aforementioned simulators here. So what is gem5 exactly? gem5 is a discrete event, cycle-accurate simulator that models computer architectures as a set or series of black boxes with latencies and attributes, all connected by various buses and ports as defined by a configuration script. So while it is not as fast as QEMU to provide you with functional results, the latencies and system configurations in gem5 can be tuned to match that of real hardware, and thus you can get performance statistics representative of said hardware within a small margin of error. Furthermore, these performance statistics can be put into a custom and validated power model to then provide good energy results, all while being much quicker to develop, verify, and simulate relative to HDL. So in addition to being cycle accurate and event driven, gem5 is also highly modular and extensible. Defining a system configuration, things like cache sizes, what devices sit on the system bus or your SoC, what CPU models to use, etc., are all defined in Python scripts. And then these Python scripts use models implemented in C++ to interface different aspects of the system. Furthermore, the models in ISA microarchitectures are all segmented, so it is possible to reuse the same hardware model for multiple ISAs. So to summarize the capabilities I highlighted, gem5 comes with numerous features right out of the box. It supports multiple instruction set architectures, or ISAs. Its CPU models, including both an in-order model and an out-of-order core model, are ISA independent, and Gem5 comes with numerous memory and device models included, things like DDR3, DDR4, cache, etc. Gem5 also has two modes of operation: syscall emulation mode, otherwise known as SE mode, and full system mode simulation, otherwise known as FS mode. SE mode is only used for running and verifying user space binaries, so if you want accurate performance results, you have to use FS mode, which simulates everything from underlying hardware components to your kernel to your file system. However, all components do not necessarily work right out of the box. System stability is not guaranteed, and a lot of disk images you find for use with full system mode, that is your file system, are relatively out of date. And it is because of these problems that gem5-X was introduced. So what is gem5-X? gem5-X is an open source framework built on top of Gem5 to simulate heterogeneous architectures, as well as a methodology to optimize said architecture. Gem5-X supports ARM full system mode simulations right out of the box with an Ubuntu 16 disk image and a precompiled Linux 4.15 kernel. Additionally, the minor, aka in-order CPU model, as well as the out-of-order core models in Gem5-X have been tuned and validated against the ARM Juno board, so these models can be used to generate performance statistics representative of real ARM hardware. Other features of Gem5-X include a gperf profiler within Gem5-X, enhanced checkpointing, 9p over Virtio support, a validated HBM2 memory model, and others. In the demo section of this tutorial, I will cover how to use the checkpointing and 9p over Virtio support, as well as being able to maintain your disk image using chroot. As a tandem project with Gem5-X, I would also like to take this time to introduce to you my primary project, Gem5 Extensions for RISC-V, or GXR5. All of the aforementioned features and enhancements in Gem5-X are targeted to the ARM ISA, but as open source hardware becomes more and more popular, there's a growing need for a Linux-capable, full system-level simulator for RISC-V architectures. Because RISC-V is entirely open source, it has none of the licensing fees associated with ARM. Therefore, the possibility of designing and fabricating your own hardware is much cheaper and easier than it would be with ARM. Unfortunately, though, full system mode support for RISC-V system-level simulations doesn't exist in Gem5 nor in Gem5-X. And so it is because of this that we created GXR5. So the preliminary release of GXR5 implements Linux-capable RISC-V full system mode into Gem5 using a Linux kernel 5.x and simple build root image. We are able to run a simulated simple board SoC based on the one introduced by Robert Scheffel's thesis and extended to model a simpler version of the Hi5 Unleashed SoC. It implements many of the missing architectural features required for RISC-V full system mode simulation, including missing instructions in both privileged and unprivileged ISA specifications, updated interrupts and interrupter models, MMU and virtual memory support, and others. So using GXR5, we are able to boot the Linux kernel and file system as mentioned, and then using this we are able to run basic benchmarks and unit tests. And finally, in a latest development, we were actually able to run a benchmark from the Spec CPU 2017 suite. Okay, so now that we've gone over the what and why, let's get into the how. I will start the demo shortly, which is split into two parts, one for Gem5-X and its enhanced features, and another for GXR5. In part one, I will show you how to set up and build Gem5-X, run your first simulation, and then how to use some of the enhanced features to optimize your workflow, including checkpointing and 9p over Virtio. In part two, I will show you how to set up and build GXR5 and run your first simulation with it. As I mentioned in the beginning of this presentation, these demos are targeted for people who are relatively new to Gem5, Gem5-X, and or GXR5. If you are not new to these frameworks but still want to see how you can extend these frameworks for architectural exploration and simulation, I would suggest again taking a long coffee break, and then we will see you at the next tutorial session. And finally, I just want to quickly mention that there are numerous resources available on the web for using Gem5 in general, as well as the Gem5-X technical manual, which is listed here for reference. Okay, hello everyone. Let's get started with the demo. So as you can see, I have an Ubuntu virtual machine up and running, and this includes a lot of the downloaded files as well as environment setup you need for Gem5-X and GXR5. In case you are running this on your own Linux installation, though, of course, the very first thing you would do after downloading gem5x master.zip and fullsystemimages.tar.gz is you do something like a sudo apt-get install and then add in all of your dependencies, and these include things like git, m4, scons, libprotobuf, python, etc. In general, I would set aside maybe 10 to 15 minutes for everything to download and install properly, of course, depending on your machine and your internet connection. But anyway, as I mentioned, I already downloaded the gem5x master zip file as well as the full system images tar.gz zip file. You'll also notice that I have a few other things in here for other demos, including gxr5.zip and rv full system images.zip. So in order to unzip and untar everything and get ready to build Gem5-X, you would of course do unzip download / gem5x master.zip, and if I hit enter right now, it would unzip into a new Gem5-X master folder just in the current directory, in this case the home directory. So if I do ls right now, you can see I have Gem5-X master already there, so that's all fine. So if I cd into Gem5-X master, you can see that I've also untarred the full system images as well as created the build folder. These things would not be there in your folder after unzipping Gem5-X master initially. To get the full system images folder, what you would do is tar/zxvf, and then go to your downloads folder, and then full system images.tar.gz, and hit enter. Keep in mind that that does include a 32 gigabyte Ubuntu 16 disk image, which you will use for running Gem5-X. And as a result, again, set aside maybe an extra 10 minutes or so to untar that folder, again, depending on your machine. So right, now that we have the Gem5-X master unzipped, as well as the full system images, if I go into full system images, you will see that there's a binaries folder and a disks folder. So if I cd into disks and do an ls, you can see that this is the Gem5 Ubuntu 16 image. And if I do that, you see that it is indeed 32 gigabytes in size. And of course, not all of this 32 gigabytes is filled with stuff. This is just so if you wanted to add your own benchmarks and binaries and other things to it, you have the space to do so, including for things like the Spec CPU 2017 suite of benchmarks. And then in your binaries folder, you see we have several files here. This includes the bootloader, a couple of device trees, as well as VM Linux. Note that it is a requirement for Gem5 to run a static version of Linux, and that's what this VM Linux file is. This is in comparison to something like VM Linux, which you don't want to use for Gem5. So, okay, all of that said, we have all of our files unzipped, untarred, we have everything in the right location. Now what we want to do is run this apply patch.sh file. So in order to do that, you do /apply patch, and then the path to your full system images folder. So you could just do something like that. You could also do export m5 path equals whatever the path is to your full system images folder. Basically what this does is that this ensures that when gem5 runs and it's looking for the disk image and VM Linux and the bootloader, etc., that it's looking in the right place. Otherwise, you're going to get system I/O errors when you start up gem5. So, okay, now that we have all that set, if you've not installed ARM GCC, GNU GCC, and that sort of thing, basically cross compilers for ARM64 systems, you will need to do that now. So on this Ubuntu image, you would do sudo apt-get install, and then like GCC ARM Linux GNU EABINF, amongst a couple other things. Again, this is all listed in the gem5-X technical manual, so you can just copy and paste from there as you see fit. But basically, once you have the cross-compiler for ARM set up, now you actually do want to make your device trees that we're going to use for this, and in order to do this, you just do make-c system ARM system ARM DT. And, well, as you can see, I've already precompiled it, but usually you get a bunch of messages, and the end result, of course, is if I do system ls system ARM/DT, we have all of these DTB files. Now, these are all device tree binaries. They basically let the kernel know what hardware is on your system when you're actually running gem5-X full system mode. So for this demo, I'm only going to use the 1 CPU ARM-v8 version of the device tree, but of course, if you wanted to run an ARM-v7 system and run it with 8 CPUs, the device tree you would be using is like the ARM7 gem5v1 8CPU.dtb. So, okay, now that all of that is set up, you should be ready to build gem5. And the way you do that is you do scons build/arm/gem5.fast. What this command does is it builds the gem5.fast binary. Keep in mind that there are actually 3 different kinds of binaries that gem5 offers. One is fast, one is OPT, and one is debug. And the way you would build those is, instead of having fast here, you would do OPT like so, or debug like so. Now, the main difference between these 3 different binaries is basically that if you just want to run benchmarks and you want to quickly get results, or get results as fast as possible, you want to use gem5.fast. However, if you want to use debug flags and maybe even put the gem5 binary into something like GDB or Eclipse, then you do need to use the OPT and debug versions, which have less optimizations and therefore are slower to run. But for now, I'm just going to stick with fast. And then another tip you can use to make compilation faster is this virtual machine I'm running uses 6 cores. So I'm going to do -J4 to use 4 cores for compilation. And then, as you see, we're going to get a lot of printouts here just checking libraries. And then it's going to check scon script files and check that everything is up to date and then compile everything. Now, I have pre-compiled this, so the compilation process, as you saw here, only took a few seconds. The first time you compile gem5, expect it to take anywhere between 20 and 40 minutes or so. But after you've compiled it once, when you recompile it, you're only ever going to recompile the files you changed, basically. And so, as I just said, the first time you compile it, it will be slow, but afterwards it will be fast, just like you saw here. And then the end result of this is if I do ls build/arm/gem5.fast, you can see that, yes, indeed, that file exists, and this is the binary we use to run gem5. Keep in mind that the build process for gem5.fast, gem5.opt, and gem5.debug are completely different. So I've not built OPT in this virtual machine yet. So if I tried running it the build command right now, it would indeed take that 20 to 40 minutes or so I mentioned. One other thing as well is that, as I mentioned previously, this build folder isn't here initially when you unzip the gem5-X master folder. You don't have to create it yourself. It will be automatically created by scons when you build gem5.fast. Now that all of that is set, we are actually ready to run gem5, and for that, in scripts I have run gem5x.sh, and basically the script is what you see here. And so first you're running the gem5.fast binary /d gem5x output. This is the folder that will contain the output of your gem5 run. The next parameter here is the config script. So this is basically, what does your simulated system look like? Like where's the hardware located? How is it connected to other pieces of hardware, etc. In general, we use fs.py for full system mode. You can create your own configuration from scratch. And there are tutorials online on how to do that, but for us it's just simplest to use fs.py because this sets up the memory controllers, memory buses, SoC devices, etc. And then CPU clock is, of course, the CPU clock, which is 1 gigahertz here. Here we set the kernel to VM Linux, which was the binary I showed off previously. The machine type we're just going to set to vexpress gem5v1. And then the DTB file, I do have a hard-coded path to. As you can see, we're going to run an ARM v8 system using only one CPU. And then this -n1 here actually specifies that only simulate one CPU. The next option is the disk image, of course, which is the same one I showed previously, gem5 ubuntu16.img. And then afterwards, you have the caches and cache options. So it's here that you could set your own custom L1 cache size, L2 cache size, associativity, etc. And there are a lot of different options associated with this. And I can show off later where you actually find these options in case you want to build your own thing. And then finally, we have system clock and memory options specified as well. So in this case, we're simulating a DDR4 module at 2400 megahertz with a memory ring of 4 and a size of 4 gigabytes. So all of that said, we are ready to actually run gem5x. So the way we do that is just bash run gem5x using the script. You could type in all of this on a command line as well, and that would be fine. Of course, you'd just be typing a lot of things, which is why I have this script set up. This script is included with the virtual machine, by the way. And you can see the result of running it is that, you know, we get the copyright notice, the notice about compilation and execution. It tells you what exactly your command line is here. So if you have a weird option or you get a weird error later on that you think could be due to the system configuration, you can always double check this. And then you usually have a bunch of information or warning notices when the system is currently set up. And then finally, real simulation, meaning your simulation has started. So all of that said, Gem5 is now running. So if I open a new terminal, I can actually connect to the Gem5 instance as though it were another machine. And the easiest way to do that is to use telnet. So you do telnet localhost 3456. And you can see here that the kernel has already started booting in Gem5X, and these are the kernel D message logs here. So this is going to take a little while to properly boot up. In general, it can take up to an hour just to boot up the kernel and the file system, at which point you should be ready to run benchmarks. So I'm going to cut here and then come back when the login screen is up and ready. Okay, and now you can see that we've reached the login screen. And at this point, we can interact with Gem5 as though it were a simulated virtual machine like QEMU, for example. So I could type ls here. You can see it echoes out the command again. And we just have this one file, mount.sh here. I could also do like print working directory and use cwrn/root. So one way I can stop it is to go back to the gem5 window where I initiated the run. You can see we got a few warnings here, but that's nothing to worry about. And you can also see that as we entered the login screen, we got this writing checkpoint message. Now, this is the first of many features in gem5-X called enhanced checkpointing. So one way I can exit gem5-X is to do Control-C here. And you can see exiting at tick this very large number because user interrupt received, and now gem5-X is stopped. Now, if I go to the home directory again, you can see I have this gem5-X output folder, and that's what I specified in the script I initially showed off. So if I go into that and do an ls, you can see that there's several files here. These config files, which basically tell you what simulated hardware is in your system and what configurations you're using for them. This system.terminal file, which is basically the output that we saw in the other window. So if I do VI there, you can see it's like the kernel dmessage output here. And then we also have this stats.txt file, and basically what that is your performance statistics. You can track a lot of different things in Gem5, but for example, if you're just worried about like how many seconds did it take to run your benchmark or something, you would just be looking at like this simulated seconds here, which in this case it simulated 152 seconds in total, even though the host number of seconds you can see was 818.4. And then the last thing you see in this output folder is all of these CPT files. And basically what these are checkpoint files. So Gem5-X is set up to automatically check a checkpoint as soon as you reach the login screen. And what that means is that it serializes the current state of Gem5-X so you can restore it later very quickly. Now, why is that useful? So say I wanted to run Gem5-X again and interact with the console some more, set up something or do something else. I don't want to wait another 800 seconds or so to reboot Gem5-X from the beginning. So instead, what I can do is I can go to scripts, and in here you see I have this run Gem5-X checkpoint.sh. And if I cap that right now, you will see that I added a couple options here. It's basically the same script, but I added this -R1 here. And basically what that means is run gem5.fast here with this configuration, but restore the first checkpoint you took. And now let me actually run this script, just so you can see the output. So you can see the normal Gem5 binary start comes up, but then right now it's taking a little bit longer to actually get to real simulation, and there we go. It says entering event queue at tick this very large number. Basically what this means is that Gem5 started at a tick much later than 0 rather than at 0. And if I go here to where my telnet connection was, you can see it exited out from the first instance being killed. But I can telnet again, and you can see I'm already at the login screen, I'm already at the command line. So again, I can do ls here and just interact with Gem5 as I want. The way that checkpointing is implemented actually is through what's called the M5 binary, which is a way you can interface Gem5-X with the host machine. So you can see where it is actually in Gem5-X, just with the which command, and you can see there's sbin M5. And if for some reason I changed something here and I wanted to take another checkpoint, I could do M5 checkpoint within the Gem5 window, and then it will make me a new checkpoint folder like we saw previously. And to double check that I did that, you can see this warning writing checkpoint is here in the Gem5 window. So on the actual simulated machine, it does take a little bit of time to run the checkpoint, but once it's over, you see we get to the command line again. Now the M5 binary does come with a lot of features that I recommend reading Gem5 documentation on, but like another one, for example, is instead of Control-C in the host window to stop the simulation, I could also do M5 exit just like that. Now, one of the most powerful features of the checkpoint feature is if I run this again, I can actually change some of these configuration options here. So, for example, the CPU model we're using in this script is the default CPU model, which we could actually double check just by going to the config file. So if I go here and I do vi config.ini, you can see this is what it looks like. And if I scroll down, you can see that we use the atomic simple CPU model by default. Now, Gem5 has multiple CPU models, including the minor CPU model as well as the out-of-order CPU model. And where the real power in checkpointing comes in is the fact that the other CPU models would take a much longer time to boot the kernel with, as compared to the atomic simple CPU. So you could boot your kernel and take your checkpoint with your atomic simple CPU, but then restore the checkpoint with, say, your out-of-order core CPU model. And then you can get performance statistics related to that O3 core model instead of this atomic simple CPU model, all while taking much less time to actually get your end result. Now, what can't you restore the checkpoint for? Unfortunately, if you wanted to change something in the disk image, you would have to start your simulation from scratch, basically. But there is a shortcut you can use to modify your disk image, or at least run different benchmarks and such without having to modify the disk image much quicker. And this is what 9p over Virtio enables. So to get started with that, you do need to install one dependency. So sudo get apt install, and then it's called diode. And then we enter the password for the conferences VM. And as you can see, I've already installed it, of course, but it's a relatively quick install. And then you want to do which diode. And you can see here that it's in user sbin/diode. And to get started, you do need to update one file in gem5-X. So if I go to gem5-X master, and then I show source dev virtio and virtual io 9p.py. This is where the Virtio model is in Gem5, where it's defined, I should say. So you can see here we have the Virtio 9p diode class definition. And one of the options we have here is this diode equals param string user sbin diode. Now in our case, I set this up previously, so I already edited this string, but in your system you may need to edit this string right here and save. And then after you've done that, you of course want to do a sconce build arm gem5.fast. It's also worth noting as well that just rebuilding gem5.fast doesn't rebuild gem5.opt or debug, so if you wanted to use those after making this modification, you would also need to run the same command for opt and debug as well. But anyway, now that we have diode edited and compiled, we can go over to our next script and cat run gem5-X 9p.sh. And so here is our gem5-X running script again, where this time we changed a couple things. The big things we want to note here is the kernel has changed, and we've also added this workload automation option at the bottom here. Now, what changed in the kernel basically is that in order to use 9p over Virtio, we need a kernel that has the 9p module installed. So we've already compiled and distributed this for you. This is vmlinux_wa, which is in that same binaries folder I showed off previously. But then we also need to add this workload automation option at the very end of our script. So what this says is that we want to have a folder shared between the host and gem5 at this location here. And you can see I set it at the home folder /script/shared. So if I do ls, you see I already made a shared folder. Now if I cd into the shared folder, I have one text file in here. Let's read it. It just says, "Hi there, HiPEAC 2021." It's worth noting that you could put basically anything in here, say like a benchmark or another binary or another text file or anything. I just have this text file here just for demonstration purposes. But right, now that we have that all set up, we do what we did before, bash run gem5-X 9p.sh. And unfortunately, this starts at the very beginning of the simulation run again. So, as usual, telnet localhost 3456. And now we basically wait for the system to boot up again, and then I can show you the 9p over Virtio features. Okay, and now that the system has booted up, you can see that we are at the command line again, as usual. If we go over to the gem5-X running window, you see we have the same warnings as before, but there's no issue there, as well as the checkpoint information. So if I go over back to our telnet instance, in order to use 9p over Virtio, we have to use this mount.sh file. So in order to use that, you do mount.sh and then the path to your shared folder, in which case this is home/conferences/scripts/shared. And we just run that in the terminal. And to double check that this worked, in the gem5 instance, we do ls/mount. And you can see this test.txt file is here from before. And if I actually cap that to see what's in it, you can see that hi there, HiPEAC 2021 file is there and intact. Additionally, I could go over to this third terminal window where I'm actually in the shared folder, and I could echo another message into a new text file. So if I cat test2, this one just says hello. Similarly, if I do ls/mount now, you can see test2.txt shows up, and I can cat it as well here. Cat it in the wrong folder. Cat it in the correct folder this time. And you see the hellos there as well. And so basically you can use 9p over Virtio to maintain your files on your disk image with relatively little overhead instead of having to restart gem5-X from right at the boot every single time. So, okay, all that said, we can now exit gem5. And then the last thing I wanted to show before we call it for this part of the tutorial is just how do you maintain your disk image. Again, instructions for this are in the gem5-X technical manual, but really the best way is to use chroot. And basically what that does is that on your host machine, it allows you to remount your root using a static QEMU build. So you can basically update your disk image or cross-compile things as though you were on the native machine with it. And so to get started with that, you of course need to sudo apt get install a bunch of things. This includes QEMU, QEMU user, QEMU system, and QEMU user static. I already have those installed here, so we don't need to run that again. Just like before, you know, a lot may be like 5 to 10 minutes or so just to install and download everything, depending on your machine. But anyway, to get started with chroot, basically we go to gem5-X master, full system images, disks, and the first thing you want to do is sudo mount the disk image. So the command is a little bit complicated, but basically we're just skipping the boot sector of the disk image and going straight to the file system. So basically you use this command to mount this disk image, and of course you need to specify where to mount it, in this case /mount. And then if we do ls/mount, you can see that our disk image is mounted here. Now before we can use chroot though, we do need to bind several of the necessary folders to actually change over the root. And so the command you use for this is sudo mount -o bind, and then we're going to use this for a bunch of folders. So the first one is proc, so we do /proc and then /mount/proc. And then we also want to do this for /dev as well. So we modify this command just to /dev and /mount/dev. Then the next one is /dev/pts. So again, same deal here, just modifying these. And then the last one we want to do is sys. So just modifying this command one last time. So we have /sys. Yep, there we go. And now we're ready to change root to our new root in the disk image. So in order to do that, we do cd mount, and then now we can do sudo chroot /. And you see now we're at root at conferences, and basically we're now in the chroot instance. We're actually in the disk image running it like it's our primary root. Like if I do an ls, you can see we have all the folders from before. If I do gcc --version, you can see that we're actually using an Ubuntu Linero 5.4 GCC version. And basically this means we've switched over to an AArch64 machine. And so from within this disk image, we can cross-compile binaries for benchmarks and whatever. You can also update and maintain your disk image this way. So like, for example, I can do apt-get update. We're already root, so I don't need to sudo or su or anything like that. And you can see I'm actually able to update the disk image files from here with no issue. And this can take like 5 to 10 minutes or so. This shouldn't take that long. So yep, see, there we go. So yeah. When you're done with chroot, you just type exit, or you can also do Control-D. And then to clean up your mount of the disk image, you need to unmount everything. So you want to sudo umount /mount/ everything we did before. So /mount/proc, /mount/sys. You want to do /dev/pts before you do /dev. And then we also want to unmount /mount itself, but you can see that in this case it says we're busy, and the reason for that actually is because we're currently sitting in /mount. So if I just do cd to home, and then I run the same command again, we can unmount it, no issue, and now we've cleanly exited the disk image. So yeah, that's everything I wanted to show with gem5-X. So now let's go over to the GXR5 demo. Okay, and so as we approach the end of this first tutorial session, I do want to quickly show off how you set up and run GXR5. Now, just a reminder, GXR5 is the RISC-V version of gem5-X at the moment, and it is still very much in a, let's say, alpha state, but it is the very first instance we know of being able to launch a full Linux kernel and file system in Gem5 full system mode for RISC-V systems. Now, if I go to the downloads folder, you can see, like before, we have a GXR5 zip file as well as this RV full system images.zip file. This is analogous to the Gem5-X master as well as full system images tar file we saw earlier. So just like before, you would go to the home directory, do unzip downloads /gxr5.zip, and that would generate your GXR5 folder, which, as you can see, I've already done and already have this folder. So if I cd into here, like before, I already unzipped the full system images folder, so we have this full system images folder you can see here, and then because I've pre-built gem5.fast and for GXR5, we also have the build folder as well. So as you can see, setup for gem5 X and GXR5 is pretty similar, but there are a few key differences though, and it mostly comes from the full system images as well as the fact that it's a different ISA. So if we actually go into the full system images folders this time and we go into disks, we don't have an Ubuntu image, but instead a build root FS. This is an ext4 rootfs, but if you've ever used build root before, when you select the ext4 option, it actually creates an ext4 link to an ext2 rootfs because both ext versions are actually compatible with each other. And it's also a relatively small build root image, only being about 60 megabytes in size. Now, if you've set up and used build root before, you know you can just change an option and rebuild it, and you can get an image of different size, but this build root image is purely for testing, just to make sure everything works fine, basically. And then the other difference also comes in the binaries folder, where you see we have this forward jump.elf file, gem5-simple rv64.dtb, and VM Linux. Now, VM Linux is similar to the one before. It's a static Linux kernel file, this time compiled for RISC-V. The DTB file has been pre-compiled in this case, but of course, just like before, you would usually use the device tree compiler to compile your own device tree structure. And then this forward jump.elf file is actually the bootloader for RISC-V, and it's based off of OpenSBI. So, okay, all that said, we can go to the main folder, and just like before, in order to build GXR5, similar to what you would do in gem5-X, you would do scons build /RISC-V /gem5.fast, and just like with gem5-X, there's also OPT and debug versions as well, and the same J4 option works as well. So you can see you get same and similar output. Again, just like with gem5-X, slot 20 to 40 minutes or so of your time to actually compile GXR5 if you're compiling this for the very first time. But as I said, as I've pre-compiled it, Scons figures out there's nothing more to compile, so it only takes a few seconds to finish this. And the other major thing you need to do as well is you need to change your M5 path. Because GXR5 and gem5-X aren't integrated yet, you can't use the M5 path you used for gem5-X initially. You have to use the one for GXR5. So in this case, we're going to do export M5 path, home /GXR5 /full system images, and that should set up everything. So now we can go over to scripts, and in this folder I have run gxr5.sh, and if I cat into it, you can see it's a much simpler system. Again, this is purely for testing and demonstration purposes, and we are adding more features as we go, but in this case we're running a single CPU RISC-V system with default L1 cache and 8 gigabytes of RAM. So in this case it's more representative of a small embedded system, which is quite common in the RISC-V space. You can also see we set the disk image to the build root.fs, as well as the kernel to VM Linux, and the DTB to this gem5-simple rv64 DTB. So that said, we run the script similar to before, so run gxr5.sh. You can see there's our whole command line right there, and then we've already entered the real simulation. Just like before as well, we can also do telnet localhost 3456. And in this case, you can see that OpenSBI actually has an output initially, and we are running the Gem5 Simple Board machine platform. Now, as I mentioned during the lecture, Simple Board is an SoC first created by Robert Scheffel of the Technical University in Dresden. We use this simple board as kind of a jumping off point for creating our Linux-capable full system mode simulator. The simple board we extended has actually incorporated features from the Hi5 Unleashed SoC, which is, or was, the first Linux-capable SoC on the market for RISC-V devices. Of course, The Hi-5 Unmatched has been announced recently as kind of a successor to the Hi-5 Unleashed, and then I've also heard that the Beagle Bone Beagle 5, I believe it's called, will be released soon. So soon there will be a lot of different RISC-V Linux-capable SoCs on the market for you to play with, and you can use GXR5 to simulate them. Now, just like with gem5-X as well, actually loading and booting the kernel will take a while. So in this case, I'll cut here and come back after everything is booted. But you can see right now that the first console Linux-D messages have popped up. Okay, now that GXR5 is booted up, as you can see, we got the GXR5 welcome message, and we're now at a command prompt. So again, just like with gem5-X, at this point in Telnet, we can interface GXR5 just like we would in gem5-X. Unfortunately, a lot of the features in gem5-X are yet to be implemented in GXR5, but they will be coming soon. Things like the enhanced checkpointing and IP over Virtio, things I mentioned. So for now, if you want to run a benchmark, say right at the startup of this system, what you can do is, well, first let's end the simulation with Control-C. Right, so what you can do is let's change directory to not gem5-X, but GXR5, full system images, and disks. And we can do sudo mount build root rootfs.exe2/mount. So we just mount the GXR5 disk image to our /mount folder. So if I do a sudo ls there, you can see everything from GXR5 there. And if we want to actually run something right at the startup, say like you cross-compiled a program or something, or you just want to double check something by echoing a text file, the easiest way to do this actually is to edit the init tab file. So in this case, I'm going to do sudo nano /mount /etc/init tab, just like that. And you can see this is what controls init for the startup of GXR5. So for the sake of demo, I have this RV hello binary that I'm just going to uncomment here. And you can see we just do the sysinit bin /RV hello, which is just this hello world binary I cross-compiled for RISC-V. So after uncommenting this, I just write it out in nano and then exit. And now I can unmount the disk image and go back to scripts. And now I can rerun GXR5 and reconnect to it with Telnet just like I did before. And I'll cut here as well and jump back to when we're on the login screen just so you can see the output of RV hello. Okay, and now that we're at GXR5, after it is booted, you can see this hello quarantine world message has now popped up. This is due to the RV hello binary running right at the start. If I run it again right now, you see it will print the same message again. Now, this can, of course, be swapped out with any binary of your choosing. In our tests at EPFL, we have used unit tests for this as well as spec. But for now, this concludes our demo of GXR5 as well as our tutorial on gem5-X. And now we will open up everything to Q&A.